Okay, so position and displacement. So what is position? Well, the symbol for position is going to be a D, so like distance, because it's related to distance, but with an arrow on top. Okay? Now, position is the distance of an object from a reference point. So this is the most important part about position and displacement, is that it's all from reference point. So you need a reference point in order to calculate position and displacement. Okay, so position is the distance of an object from a reference point, including the object's direction, because it is a vector quantity. Okay, now the arrow over top of a symbol represents that it's a vector quantity. So there's a difference between D versus D with an arrow. This is distance, scalar. This is a vector, this position. Now displacement is delta D with an arrow. Delta means change in. And we'll get into what change in means when we look at the equation. So displacement is delta D with an arrow on top. Now displacement is the change in position. Okay, so it's a change in position of an object, including the object's direction, because it is a vector quantity. Now, an arrow over top of a quantity symbol means vector. So arrow over a symbol means that it's a vector quantity. So you have to pay attention to when you're writing your symbols down, that you're using the appropriate symbol, whether it's a scalar or vector quantity. Calculating displacement. There are two different ways of calculating displacement. So if it's just a trip between point A and point B, so you're going from point A to point B. So just a one-way trip, there's a beginning and there's a definite end, okay? Displacement, remember, was delta D with an arrow. Now delta means change in. So this is change in, which is the triangle, the delta, and it's the position symbol, change in position. So delta D with an arrow, delta means change in, the D with an arrow means position. So by definition, the symbol actually tells you what the definition is. It's change in position. Now, whenever you're doing change in, you're always going to do the final minus the initial. Now, we've seen this before. So if you look at delta y over delta x, delta, if this was slope. So from grade 9, slope is delta y over delta x. Delta y, the change in y is y2 minus y1. Change in x is x2 minus x1. So you always take your second quantity minus your first quantity, or what we're going to do is your final quantity minus your initial quantity. Okay? Or delta D equals D2 minus D1, or DF minus DI, your final position minus your initial position. Now it's important to note that these subscripts, so if I have DF, okay, F is a subscript, okay, all it is a note. Okay, so it's like, okay, this is position, but this is my final position. It actually has no mathematical meaning. It's just a way to give us notes on the type of variables we're using. As you can see, there's two different types of positions. There's your final position and your initial position. So how do we differentiate? If I just use D, there'd be no way to differentiate between the 2 points. So what I do is say, okay, well, DF, and then I use DI. To initiate to tell the reader that it's my final position and my initial position. Okay, now let's say I have multiple displacements, B, multiple displacements between A, B, C, etc. So this could be like you going from A all the way to B and then back to C. Okay, so I have multiple different displacements. So what we can do is add them together. So your displacement, there's actually an error there. your total displacement is equal to your displacement 1 plus your displacement 2 plus, and you can continue going. So for example, in the example that I drew, your first displacement is from A to B. Your second displacement is from B to C. And you could continue doing this for as many displacements as you want. So if we have just a one displacement, so from point A to point B, then you do the df minus di. If you have multiple displacements, so you're doing multiple trips between multiple points, then you do your displacement is your first displacement plus your second displacement plus your third displacement, etc. So in here, I want you to add the deltas to mean displacement, not positions. Okay. Now let's go through some examples. So displacements between 2 points. All right. So trip A. So there's a diagram up above. Okay. So you're going to go from home to school to McDonald's, and home is your reference point. So remember, whenever we're talking position or displacement, we need that reference point. It's all about that reference point. So here, home is my reference point. Okay, so I'm going to put a star there. Let me get it out of the way a little bit. So here is my reference point. So what's the distance traveled? Well, I went from home to school. That's 200 meters. This is 250 meters, and that's 300 meters. And then I went from school to McDonald's. Okay. So I traveled 200 meters. Then I had to travel back home, which was 200 meters. Then from there, I had to travel 250 meters. So when I add that all together, you're going to get 650 meters. Now remember, distance is scalar. There's no delta. It's just d. Distance is scalar, so there's no direction. It's just a magnitude. So my answer there is you traveled a total of 650 meters. Now, what is your initial position? So di or d1, your initial position. So you started off at home. Now, position is how far are you away from a reference point. So if I started from home and I'm at home, how far am I away from my reference point? And the answer is 0 meters. Now remember, position is a vector quantity, so you also have to have a direction. So because there is no direction, because 0 is anything, you're just going to put 0 meters west. It doesn't matter. Okay, it's just 0 meters. Now let's look at our final position, D2 or DF. Okay, now where do I end up? I end up at McDonald's. So how far are you from your reference point? So how far is McDonald's from your reference point, which is home? And the answer to that is it's 250 meters, right? And 250 meters away from my house in the westward direction. So north, east, south, west. So I'm 250 meters west of my reference point. Okay. So now what's my displacement? So remember, displacement, delta D, is your final position minus your initial position. So what was my final position? 250 meters west minus your initial position, 0 meters west. Now here is probably one of the most important concepts when we're dealing with physics, is the idea of positive and negative directions. So what I want you to do is get your calculator out, and I want you to find the west button on your calculator. Okay, or the north button, the south button, the east button. So go take a moment, look throughout your calculator. You need to find the west button. So I'll give you a moment, pause the video, and then go look for it. Okay, so hopefully you took the time to look for it, and you were there for a couple minutes until you realize there is no west button on the calculator. There's no north button, there's no east button, there's no south button. So how, if in a calculator there is no west button, there's no north button, how can I calculate this? Well, this is a very important concept. What we have to do in physics is we have to convert directions to positives and negatives. So you have complete control over this. What I am going to say, if you go on the top right, I'm going to say anything north and anything west is positive. That means east is negative. That means if I traveled south, that would be negative. If I traveled west, that would be positive. And if I traveled north, that would be positive. So in each direction, north-south, you have a positive and negative. And then in east-west, you have a positive and you have a negative. So now that I know that west is positive, you see how I put 0 meters west? Well, instead of west, west is positive. So it's plus 0 meters. And instead of saying 250 meters west, west is positive. So I'm going to put positive 250 meters. Now here's a big difference between physics and math. Here's the big difference here is positives and negatives for almost all concepts, except one concept of voltage, which you do in grade 12 physics, okay? Positive and negative literally just mean a direction. We have been so accustomed to this number line that if I say positive 5, so that's 0, and negative 5, we have been accustomed to saying negative 5 is less than positive 5. That is not true in physics. Negative 5 equals positive 5, just in opposite directions. Positive 5 is in the positive direction, negative 5 is in the negative direction. But the magnitude itself is 5. So whether I went 5 meters west or 5 meters east, I still went 5 meters. The positive or the negative literally just means the direction. Okay? So this is a concept you're going to have to get familiar with. All right? So then to do this, I'm going to have positive 250 minus positive 0, which is just 250 minus 0, which is positive 250 meters. Now remember, I got positive 250. So in this case, what is my final answer? Well, it's 250 meters. Positive meant west. Okay? So we convert directions to positives and negatives just to be able to do our math. Once we finish our math and we get our final answer, we convert the positive and negative back into a direction. Okay? I want to see both of those answers. I want to see the positive and negative version, and then I want to see the version where you converted it back to a direction. So let's go through another example here. Home to school to McDonald's. So I went from home. I went from home to school, and then from school to McDonald's. So it's the same trip that I did in the previous question. But what I'm changing is my reference point. Your rocket is your reference point. You have to remember that whenever you're dealing with vectors, you need the reference point. So the rocket is my reference point. Now let's calculate the distance traveled. So I went from, so just to clarify this is 250, that's 200, and that's 300. So I went from home to school, so that's going to be 200 meters. Now to go to McDonald's, I got to travel that 200 meters backwards, and then I got to travel the additional 250 meters. So that's 650 meters. Now remember, distance is scalars, direction doesn't matter. Okay, initial position, D1 or DI. Now because I'm doing this, I get to label whatever I want. So because I'm going east-west, I'm going to label west as positive. Okay? I'm going to label west as positive. So when I say I had my initial position, so where did I start? I started at home. Okay? How far am I from my reference point? Well, I am 500 meters west of my reference point. My reference point is my rocket. So how far am I from my reference point? 500 meters in the westward direction. Now remember, we can't actually deal with west. So we have to convert this into a number that we can actually use for a calculation. So I'm going to convert this. West I put as positive, so it's going to be positive 500 meters. Now my final position, I ended up at McRonald's. There I am. Okay, now what's my final position? Well, how far am I away from my reference point? So my reference point is the rocket. So I am 300 plus 200 plus 250. So I am a total of 750 meters west, which is west is positive 750 meters. Okay. Now, calculate the displacement. Your displacement is your final position minus your initial position. So my final position is positive 750 meters minus my initial position of 500 meters. So 750 minus 500 is positive 250 meters. Now, because that's positive, I'm going to change that direction back to west, because west was positive. Okay, so in general now, which quantities are tied to the reference point? Well, we have position and we have displacement, because displacement depends on position. Which quantities are not tied by the reference point? And that's distance. No arrow, no vector quantity. Okay. Now, let's go back to our previous example with Anastasia from the previous lesson. So Anastasia lives down the street from school. She walks from home to school and from school back home every day. So as you can tell, diagrams are extremely important in physics, because what we are doing in physics is essentially just saying this is what we are seeing. Now we have to make sense of it. So it's really important that we draw what we see, and then as we draw that diagram, we're going to start putting numbers into the diagram. Physics is about taking and studying what we see and just quantifying it. So drawing the diagram is extremely important for every question that you do. So here's your house, there's your school, and the house is 4.5 kilometers away from the school. So what you did is you walked to school, back home every day. Now I want to calculate the displacement for Anastasia's walk to and from school every day. Now remember from the previous lesson, we said this was 0. We didn't explain why. We said this is called displacement. So now we understand what displacement is. We are going to show why. So your displacement is your final position minus your initial position. So in order to calculate your displacement, I need my positions. In order to find my positions, I need a reference point. Now, as you saw from the previous example, we changed the reference point. So here rocket was the reference point, but here home was the reference point. We had the exact same trip. So we went home to school to McRonald's. This one went from home to school to McRonald's. So the only difference between this question and this question was the reference point. So here home was the reference point. Here the rocket was the reference point. Let's compare. The distance traveled was the same, 650 and 650. The initial position here was 500 meters west. The initial position here was 0 meters west. The final position here was 250 meters west. The final position here was 750 meters west. So changing the reference points changed my position values. Now let's look at the impact on displacement. So if I looked at my final displacement here was 250 meters west. My final displacement here was 250 meters west. Okay, so changing the reference point does not change your final answer. So what that's telling us is when we're calculating displacement, we have control over the reference point. No matter what the reference point is, our displacement won't change. So when we're going to this question here, I need a reference point, but the question doesn't give us a reference point. The previous questions did. So why don't I just go pick a good rule of thumb is always pick your starting point as your reference point. It just makes math easier. So it's just easier to pick your starting point as your reference point. So when I do this, my DI, how far am I at my reference point initially? So I'm at home. How far am I away from there? 0 meters. Now, when I get back home, so I go to school, and then I get back home, I'm going to be 0 meters away again. My final position, I'm back home again. Okay, now these technically need directions. Okay, so because of that, you also have control over your direction. So I'm going to say west is positive. So that means east would be negative. Okay, so that's going to be positive 0 meters. That's going to be positive 0 meters. So let's go back to our equation here. My final position was 0 meters. My initial position was 0 meters. 0 minus 0 is 0. Okay, so your delta dt, so your total displacement, is 0 meters. Now, how does that make sense? Well, look back at the definition of displacement. Displacement is the change in position. Well, I started off at home and I ended up at home. So what was my change? Nothing. So this is the big thing about vector quantities. It's always calculating, essentially think about it like efficiency. Sure, you traveled a total distance of 9 meters, but effectively, what did you actually do? And at the end of the day, to your parents who might have left work before you went to school and who got home after you got back from school, they have no actual proof that you went to school. They came home, you were on the couch. They came back home, you were on the couch. 6 hours, 8 hours had passed, but at the end of the day, you had not moved. So your total displacement was 0. But in reality, your distance traveled was 9 kilometers. Sorry, this is in kilometers, not in meters. My mistake. Okay. And that's how you can calculate that. Now, there is another way of doing it. Because remember, we do have multiple displacements. I went from home to school and from school back home again. I'll do that in a separate video just because so I'll have more room. But I'll show you the second way of doing that after. So 2 multiple displacements. Okay. So calculating displacements with multiple displacements. So first I want to cover it before I show you. So consider a trip that involves 2 displacements. So you went 700 meters west and then you went 500 meters west. Calculate the total displacement. Now there are 2 methods in order to do this. There's the vector scale diagram method and then there's the algebraic solution. So vector scale diagrams. So what you're doing is drawing a diagram to scale using vectors, okay? So vectors show the direction. So number 1, draw vectors to scale. And so first thing you have to do is create a scale and add them tip to tail. So what does that mean? Well, first off, let me create a scale. So I'm going to say 1 centimeter, okay, is 100 meters. So every 1 centimeter on my diagram is going to be equal to 100 meters. So what I'm going to do is, because I'm traveling west, I'm going to start off over here. So this is my starting point. My first thing was 700 meters west. So I'm going to draw a line that is about 7 centimeters long. Okay, so call that 7 centimeters. All right, so to do this, what you would do is 700 meters times our unit factor. So 100 meters and 1 centimeter. Meters and meters cancel. So 700 times 1 is 700 divided by 100 is 7 centimeters. So that's how you can convert from your value using your scale, using this unit factor that we did in the introductory unit. So that's 7 centimeters to the west. Now here is how we draw a vector. So this is the tip, with the arrow, and this is the tail, okay? Now, doing tip to tail, I'm gonna get my second displacement, which is 500 meters, so it's gonna be 5 centimeters long. When you do the conversion, you'll get 5 centimeters long, and this is where you end. Now, in a perfect world, you would have a ruler. I'm doing this on an iPad, so it's really hard to, my iPad's not big enough, like a sheet of paper. So I can't really draw this to scale, but here's the idea. Now what you would do is go from here. So go from your starting point to your ending point. That's your change in position. That's your displacement. And you would measure out that line. And when you measured that line out, you would get 12 centimeters. Okay? After that, you would convert that 12 centimeters using your scale. I need to cancel out centimeters. So centimeters on top, cancel out with centimeters on the bottom. Put meters on top. Now through my scale, I said 100 meters is 1 centimeter in my diagram. So you're going to get that 1200 meters west. Okay. So that is a vector scale diagram solution. Something that can be used but not often used. What the more appropriate measure to use here, the method to use here, is the algebraic solution. So this is when we're going to do it strictly just using math. Okay? So because I have multiple displacements, I have 2 displacements, one of 700 and one of 500. So my first displacement is 700 meters west. My second displacement is 500 meters west. So from my definition, using multiple displacements, you can get your total displacement is your first displacement plus your second displacement. And you can continue going for as many displacements as you have. So now when I plug this in, I'm going to get 700 meters west plus 500 meters west. Now remember, your calculator does not have a west button, so it is important to note which direction is positive, and you have total control. So just to change it up, we've always said so far west is positive. Let me change it up just so I can show you how it doesn't matter. Let's put east as positive. You have full control over your direction, which one is positive. It's just important for you to write it so the user knows, so the reader knows, okay? So whoever's actually reading your solution, they can actually say, okay, yeah, east is positive. So now what I have to do is convert these into into numerical directions. So 700 meters west is now negative. If east is positive, west is negative. So this is going to be negative 700 meters. And 500 meters west is going to be negative 500 meters. Because west is negative now. I've made east positive. So when I do this, this is going to be negative 700 meters plus negative 500 meters. When I add those together, you're going to get negative 1200 meters. Because positive and a negative make a negative. So you're going to get negative 1200 meters. So that is one final answer. But remember, I want you to convert this back. Displacement is a vector quantity, so it needs a direction. Negative, in this case, was west. So it's 1200 meters west. Now, if I compare to my answer that I got using my graphical solution, my vector scale diagrams, I got 1200 meters west, and here I got 1200 meters west. Okay, so what you're seeing here is there's 2 different ways of doing it. The algebraic method ends up becoming more widely used just because it's a lot easier than drawing diagrams to scale, especially when we get into 2D. These are 1D diagrams because they're only moving in one direction, one dimension. They're moving east or they're moving west. There's no east and north. Okay, so they're only moving along here. I have not included a vertical component to it as well. So here's what we call one dimension. So either one is kind of good. Get used to doing the algebraic solution because especially when we get into 2D, motion, which is like saying you're moving this way, then you're moving that way, vector scale diagrams become a lot more challenging because you need protractors and it becomes less accurate. So algebraic becomes the way that we do it, okay? So just get comfortable practicing with the algebraic solutions. It's more widely used. So now I want you to give it a shot. I want you to do example 4. I want you to do it using multiple displacements. So you have displacement 1 here, and then you have displacement 2 coming back. I want you to try it. You should get your final answer still to be 0 kilometers. So give it a shot. Don't forget about your directions, and good luck.